The Evolution of Cryptography.
One very basic type of encryption is called the Caesarian shift. Basically, every letter in the word to be encrypted is shifted over a certain number of times in the alphabet. For example, the word blue with a shift of 3 becomes EOXH. Another type of encryption is called key text substitution. First, an arbitrary phrase is chosen to be the key text source. The first letter in each word of the key text source is given a number in order starting at 1. Then each letter in the word to be encrypted is set to the corresponding number. The key text source must contain all the letters in the word to be encrypted. For example, the word blue becomes 6234. Another type of encryption is called the Vigenère cipher. This type of encryption uses a table called the Vigenère square and an arbitrary code word. To encode a word, the encoder follows the column corresponding to the first letter in the code word until they reach the row of the first letter in the word to be encoded. Where these two meet is the encoded letter. Continue this to encode the whole word. For example, blue becomes MPNP using the code word let. Notice that even though no letters are repeated in the word to be encoded, there are letters repeated in the encoded word. This works both ways.
Public key cryptography utilizes an asymmetric two-key relationship rather than one symmetric key. This means one key is to be shared freely, while one key stays private with one party, rather than both parties keeping the same private keys. So if the public key encrypts a message, only the private key can decrypt it, and vice versa. However, since a public key is public, the key has to be strong enough to withstand brute force methods of decryption, so not to reveal the private key. Using the asymmetric pair key method requires far too much computation to encrypt an entire message. Rather, the same goal can be achieved by creating a new session key with the asymmetric key method. This session key is used to encrypt the rest of the message. Along with the message, an encrypted hash value is sent to be checked with a calculated hash value of the unencrypted message. This serves as a digital signature. RSA utilizes the public key method. Since the keys are derived from multiples of very large prime numbers, the private key can only be found through the public key by factoring the multiples of very large prime numbers. Because the amount of brute force required to factor such large multiples is not easily achieved, the private key cannot be discovered through the public key.
There are several risks to the modern implementation of public key encryption (RSA), including the brute force approach, Trojan horse attacks, and passive attacks. The first method of breaking RSA encryption, the brute force approach, uses large amounts of computing power and the most advanced factoring techniques. In 1994, using this method, 600 computers working together for 8 months broke RSA-129. However, programmers could always just use higher values for prime numbers used in the encryption process. Another method of breaking RSA is a Trojan horse attack. A coder could create a program that acts and feels like a legitimate program that takes the user's password and private key. However, it would be very difficult to implement this kind of program without raising any flags, and only the incoming messages could be decrypted since only the sender's private key is known. Passive attacks are also a big threat to decrypting RSA. These do not hope to break RSA, but to subvert the encryption itself. One of the largest threats is keystroke snooping. This kind of program records the user's keystroke so that passwords that grant access to the RSA client can be compromised, letting the hacker view all the messages decoded. So therefore, the weak point of RSA is actually the weak implementation of this strong system. For everyday users, RSA is acceptable. However, with the invention of new technologies, RSA may be rendered obsolete.
As the strength of modern computing continues to increase, the strength of RSA encryption weakens. The development of quantum cryptography combats this flaw. Quantum cryptography makes use of quantum mechanics in order to ensure a secure communication. The concept relies on the Heisenberg uncertainty principle, whereby the state of light particles, or photons, in pairs of varying orientations cannot be differentiated with complete certainty. Eavesdroppers who try to intercept a signal between a sender and a receiver will have a hard time avoiding detection because there is a 50% chance that they will cause an anomaly in the signal transmission with each wave of particles they try to measure. However, two reasons exist for the slow deployment of these systems. The first is that special hardware is required to send and receive photons. At this point in time, there is no practical solution for businesses, and such hardware setups are very expensive. The second reason is that the distance of communication is not long enough to be practical, since the states of photons are easily disturbed. However, recent developments in optic fiber have solved this second hurdle.